Most LTR models fail because the features are wrong, not because LambdaMART is wrong. This is the setup you'll be able to run after this, which turns a query, documents, and clicks into features and reports offline ranking quality. I'm Professor Pi, teaching search and IR with simple Python. Search re-ranking is where feature engineering wins or loses. People reach for OpenSearch learning to rank because it plugs into an existing search engine and lets you add behavioral and lexical signals as features. Success looks like better top results for real users while keeping latency reasonable. We will work with a tiny, repeatable example so you can see the full pipeline. Index documents, pull BM25 scores, add click-based priors, avoid time leakage, and measure offline lift. That makes concepts concrete and gives you a template you can scale. The idea is simple. Start with BM25 scores from OpenSearch as a strong lexical baseline. Add a stable behavioral prior derived from past clicks to nudge ranks where lexical signals are weak. Build features that are computable both at serving time and during offline training. Evaluate with an offline metric that mirrors user satisfaction. Now we will seed the tiny index. Now we'll create a tiny working corpus. This snippet creates a tiny working corpus by sending REST calls to OpenSearch with the requests session. The variable base holds the OpenSearch URL, and S is the reusable HTTP client. Two documents are indexed into the LTRX index using the Put Document API, each containing a short title T, a body field B for BM25, and a clicks counter to stand in for engagement. A refresh call makes the documents immediately searchable, so later queries return them. The printed doc's seeded value confirms the corpus is ready for feature extraction. Next, we'll run a query and gather BM25 scores and click values. This example adds a third document, refreshes, and issues a match query on the B field using OpenSearch's _search endpoint. The response R includes hits with BM25 scores in the score field. The variable feats collects training features per hit, the document ID, the BM25 score, and the clicks value from the source. This compact feature row mirrors what you would log in production current query score plus a stable behavioral prior. The printed BM25 rows confirms how many rows were extracted for this query, giving us a baseline feature matrix to build on. Now, we'll build a tiny re-ranker that blends lexical and behavioral signals. This code builds a simple re-ranker by blending BM25 with a smoothed click prior. The variable W controls how much the click signal influences the final score, and math.log1p dampens large counts to avoid a few documents dominating. The sorted call orders feats by the combined value, with reverse ensuring higher scores rank first. The variable rare contains the new ranking that can be compared to the BM25 only ordering in feats. Increasing W emphasizes behavioral evidence more, potentially improving head queries at risk of bias. Decreasing W keeps ranking closer to lexical relevance. The printed IDs show how the top document changes with this blend. Next, we'll simulate timestamped clicks and enforce a cutoff to prevent leakage. This snippet simulates click events EV as time doc ID clicks and applies a cutoff cut to avoid leakage. The list IDs pulls the current candidate documents for the query from feats. The dictionary cry computes for each candidate the sum of clicks at or before the cutoff, which represents a historical prior that is safe to use at training time. Using only pre-cut data prevents you from peeking at future behavior when generating features. The printed prior use total confirms how much training signal will influence the re-ranker. while respecting temporal boundaries. Now, we will recompute the re-rank using only leakage-free priors and measure offline quality. This example evaluates impact by recomputing the re-rank R2 using the leak-free priors PRI and measuring NDCG from held-out clicks. The Dictionary Lab aggregates post-cut clicks as relevance labels for the current query's candidates. The lists L and L2 map those labels to BM25 and re-ranked orders, respectively. The function F computes DCG with a log discount, and Z normalizes by the ideal DCG to yield NDCG. If you increase W, the model leans more on priors and may help head queries. Decreasing W keeps results closer to lexical scoring. The printed NDCG values show the re-ranker's offline lift over BM25. Mapping this tiny example to a live system is straightforward. Replace the 2 or 3 documents with your full catalog. Replace the simulated events with real click logs, and store pre-computed priors in your feature store for fast lookup at query time. Recap in 3 points. What it is: a practical LTR feature pipeline that blends BM25 and a smoothed click prior. When to use it: when you have reliable historical engagement and you want safer, measurable offline gains over BM25. One caveat: behavioral priors can bias results if not time-gated or smoothed, so always prevent leakage. Next step: tune the blend parameter W and measure NDCG across queries to find the sweet spot between lexical relevance and behavioral signal. If short, practical IR helps, subscribe and watch the IR videos.